Any general questions, problems, anything? I did. What happened to it? Anything? Yeah, okay. Again, we're talking colligative properties, and by definition, a colligative property only depends on the concentration. And so, in general, for boiling point or freezing point, right, there's a direct relationship between the change in the phase change temperature and the molality. Right, we saw for vapor pressure, the dependence on vapor pressure was directly proportional to mole fraction, which is just a different unit of concentration. All right, the Kf or Kb is a solvent property, and really you're just trading off concentration for change in freezing point or boiling point. Right, I mean, this pops up all over the place. We talked a little bit about throwing ice on the driveway. If you did the homework, you threw ethanol in the driveway. Again, it doesn't really matter what you throw on the driveway. Well, it doesn't matter from a de-icing standpoint. It matters from a cost standpoint, usually environmental standpoint, right? And salt is used just because it's cheap, and also because unlike sucrose, sugar, which we saw a minute ago, it's a smaller molecule, you get more bang for your pound. And so you don't need to throw quite as much material out there. Okay, but the key here is it does not care what the identity of the solute is. And so that includes the fact that it does not care if it's even a whole molecule. Right, since the colligative properties only depend on the number of solute particles, it does not really matter whether it's a whole molecule or a piece of a molecule, or quite frankly, 10 molecules stuck together. Right, it's a total number of pieces. And so more generically, the freezing point or boiling point depend on one other property, which is actually a solute property called the Van 't Hoff factor, which is really a ratio of the moles of particles relative to the actual concentration. This can work both ways, right? In the sense that some molecules stick together. And so if you have two molecules that form what's known as a dimer, and so, one caterpillar is stuck to two caterpillars, right? If these are actually stuck together, right, they act as a single particle, a single bigger particle, but size not as big an issue here. And so, if you had 2 molar of A's, right, they act like 1 molar of dimers because I have half as many particles because they're stuck together. And so in that case, the Van 't Hoff factor would be half. It's really a concentration correction for particles that are sticking together or falling apart, right? One of my other big themes that I keep promising you, and here it is yet again, right? Ionic compounds, when they dissolve in water, dissociate. You cannot say that enough times. All right. As a result, if I have sodium chloride, for example, which is an ionic compound, and I dissolve it in water, I don't have sodium chloride anymore. I have sodium ions and chloride ions, and they're mostly not together. Right? I say mostly not together because they are oppositely charged species, right? And so they can sort of stick together a little bit in what's known as ion pairing, right? This is in some sense similar to my dimer formation, right? As a result, right, sodium chloride, which mostly falls apart into two pieces, doesn't end up giving me a total of two pieces because of the ion pairing. As you might expect, right, dimer formation or ion pairing, right, are concentration dependent. If I have way more ions floating around, it's far more likely that two of them are near each other and have an opportunity to pair. And so Van 't Hoff factors are concentration dependent, right? And so I always have essentially two Van 't Hoff factors. There's the one I expect to get, and there's the one I actually get, right? And, you know, in a pinch, I might only know the one I expect to get, right? Because this is the actual number of pieces I would get. At very, very dilute solution, where it becomes less likely that they find each other and therefore stick together, right? The sodium chloride should give me two pieces, right? The magnesium sulfate should give me two pieces, right? The iron 3 chloride should give me four pieces, right? But as the concentration starts to go up, they start to ion pair. And so you'll notice this refers specifically to a 0.05 molal solution, right? By the time I'm at 0.05 molal, there's some ion pairing going on for all of these, right? And so the actual sodium chloride Van 't Hoff factor I expect at 0.05 molal is 1.9, right? The problem, of course, is, again, it's one of those pieces of data I don't have an infinite amount of data for, right? What if it's 0.055? What if it's 0.03? What if it's 0.1, right? And so sometimes, again, I default to the expected because it's the only piece of information I had. Or in this case, since I know at 0.05 molal it's 1.9, I might use that for concentrations near 0.05, even if it's not going to be 100% accurate. Right. But it does increase the effectiveness of an ionic compound as a suppressor of the freezing point or an increaser of the boiling point, because I do get more pieces per molecule. Right. And so, right, if I use magnesium chloride in water, again, it should change the freezing point. How much? Well, more than just the molality of magnesium chloride would suggest, because again, magnesium chloride is an ionic compound. If it's dissolved in water, which it has to be for this to work, right? Otherwise, I don't have a molality in the first place, right? The fragmentation gives me a Van 't Hoff factor of close to 3, right? 2.7 as per my table, all right? Again, I may or may not be at 0.05 molal, but I'm going to assume that's close enough as it's the only data point I have. All right. And if I do that, I get the same cheerfully simple problem to solve. The delta T of freezing, the difference in the freezing point between pure water and my magnesium chloride solution, is given now by minus I the Van 't Hoff factor for an ionic compound, the Kf, which is still a water-only property, and good old molality, which is moles of magnesium chloride per kilogram of solvent. All right, and if I do that, all right, I get that the freezing point is depressed at teensy-weensy, in this case, 0.17 degrees. That's a fairly dilute solution, right? For something like ethanol, which was on the homework, or ethylene glycol or sucrose, which we were using on Wednesday or Monday, the Van 't Hoff factor is simply 1. Right? Covalent compounds do not dissociate, right? And most of them do not form dimers, right? And so, you know, more generically, I should probably always write it this way, but for non-ionic compounds, I is 1, and so I don't really need it. All right, and if I do it, right, for boiling point, we talked about how the reason it's a colligative property is because there's a surface blocking phenomenon from the solute molecules, right? And I mentioned very, very quickly, flashing forward to this slide, right, that there's a similar microscopic view of the freezing point depression, right? The reason it ends up being a colligative property is because having the presence of a solute in the liquid gets in the way of lattice formation for the solid. When I'm freezing, my molecules all start sticking together, right? How exactly they stick together depends on their shape and the intermolecular forces, right? For something like water, you're going to maximize the hydrogen bonding, and they're all going to stick together, you know, where the oxygens are near the hydrogens, right? But to form that lattice where the molecules are all sticking together, now maximizing their intermolecular forces, if I've got another molecule present, it gets in the way of that formation, and therefore I have to get colder before I can get the lattice to form. And so it's a somewhat similar mechanism to the vapor pressure, but instead of the need to cross the interface and go from liquid to gas, I have to go from liquid to solid lattice. And again, my solute is just essentially statistically blocking sites. Right? Yes, no? Right. And again, if we look at the sucrose issue relative to the salt issue, you can see why sodium chloride, right, gets used instead of sugar, right? We did this problem on Monday, right? If I have sucrose or anything else for that matter, right, to get a 3-degree change in freezing point, I need a 1.61 mol solution, which ended up being 55 grams of sucrose. Right? If I try to achieve the exact same change in freezing point using sodium chloride, right? It's the same amount of water, it's the same freezing point, it's a different solute, right? Again, the big thing here is sodium chloride gives me almost 2 full pieces for each molecule, so I essentially have twice the molality, well, 1.9 times the molality. It's also a smaller, lighter molecule, right? And so right off the bat, because I get 1.9 pieces, I only need a 0.8 mol solution instead of 1.6, but the molar mass is also only 58 grams, right? And so the total amount of salt that I need is about a factor of 7 smaller, right? Or no, almost 10 smaller, right? And so that and associated cost per pound, is why sodium chloride gets dumped on the driveway rather than sugar, even though you can make a case that sugar is environmentally better, right? I mean, you're probably not interested in feeding insects, right? Or I suppose any other number of vermin might be licking your driveway if you've been sugaring it all winter, right? But, right, sugar is essentially a nutrient in the environment, right? Salt is actually toxic to most life forms due to osmotic pressure, which we will talk about in a minute, right? And so ionic compounds, slightly special, right? Because of the Van 't Hoff factor and the fact that they dissociate when they dissolve. Right. Yes, no, maybe. Those are really the most important three of my colligative properties, especially in the context of what we've been talking about, which has been phase, right? The phases of my solutions are going to be different than the phases of the pure liquid, right? If you salted your driveway has liquid water on it, whereas your yard has frozen water on it, even though it's the same temperature. That's the practical everyday view of things. You know, laboratory wise, if I'm trying to boil, well, maybe I don't, well, we can boil it. I was going to say, I don't even necessarily need to boil it, but right, if I want to boil my solution, I'm going to have to go above 100 degrees by the very nature of the fact that it's a mixture, right? And so in the context of what we've been talking about, those are the only three that really matter. Osmotic pressure, if we had tests, it wouldn't be on it. Since we don't have tests, nothing's on it. But I don't consider osmotic pressure per se to be that important as a colligative property. The only reason I mention it is because A, it does exist, and B, it does pop up in biological settings. All right. From a straight colligative property standpoint, I don't consider it that important, in part because it's somewhat artificial, right? In terms of the actual functional math, it looks a lot like the ideal gas law, except they use a Greek P, pi, right, in good old PV equals nRT. And so if I rearrange that slightly, where the N is now moles of solute instead of moles of gas, and the volume is the volume of the solution rather than the volume of the gas, right, I end up with this osmotic pressure being proportional to the molarity, yet a different concentration unit. Right, now I say it's artificial because here's the thing, right? If I've got a solution, its freezing point moves. If I have a solution, its vapor pressure moves. If I have a solution, its boiling point moves. My other colligative properties exist as soon as I simply have a solution, right? Osmotic pressure is meaningless for a solution, right? The only time you see it is when you have the somewhat artificial situation where you have two solutions which happen to be separated by what's known as a semi-permeable membrane, meaning only the solvent can cross it, which in our case, since we've been talking about aqueous solutions, means water, right? Having two solutions in the semi-permeable membrane is a somewhat special setup, right? My freezing point and boiling point colligative properties always exist as soon as I mix anything into my solvent. The osmotic pressure is meaningless unless I construct this somewhat artificial setup. The reason it becomes important is because what in the lab, the chemistry lab, would seem to be a somewhat artificial setup that I had to construct exists naturally in cells, right? Cell membranes are semi-permeable. And so biologically, you always see osmotic pressure. right? The word gets shifted slightly in a lot of biological contexts, and it's referred to as osmosis because of what osmotic pressure ends up causing to happen, right? And so for that reason, it's worth talking about. You may see it again if you're of a biological bent. From our standpoint, I don't have a lot of membranes, right, in most of my chemistry. There are times you do, right? It's a way of purifying water, for example, reverse osmosis, as it's called, using a membrane, right? But for the most part, I'm mixing stuff together and cooking it, trying to make new compounds. I am not constructing what's really a physical arrangement, trying to get water to flow. And so what it really says is, if I have two different concentrations of anything, I made this sodium chloride, but again, could be anything, right? There's a difference in osmotic pressure in the two solutions due to the different concentrations. And because of the membrane, the system can actually seek to correct the imbalance. And so since only the water can flow, right, you end up with water pressure flowing from the 1 molar side to the 4 molar side. And it'll keep flowing until the concentration is equal across the membrane. Right. Again, you can see how this is essentially strictly statistical. You've got more water on one side than the other. And so, frankly, water is flowing in both directions, right? Because it can pass the membrane. If it bumps into it in the right orientation with enough energy, it goes through. Like anything else, molecules don't choose. They don't know which side they're on. But because one side has statistically more water than the other side, there ends up being a net flow left to right in this case, right? If you calculate the osmotic pressures, they are relatively substantial, right? A 1 molar solution of sodium chloride, so there's my Van 't Hoff factor again, has a 48 atmosphere pressure, right? Whereas in the 4 molar side, it's 190 atmosphere of pressure. So you would end up with a net 142 atmospheres. I don't know why my arrow turned into a question mark, but blame Microsoft. A net 142 atmosphere flow from left to right. The direction of the osmotic pressure is actually towards the solution that generates it, right? This is an actual physical force. You can use it to push things. There's a somewhat famous, and I can find it, it's a pretty boring video, the one I keep finding, but there's a pretty famous, again, artificial contrivance known as a sugar fountain. All right, and essentially it uses osmotic pressure and just a sugar solution generating the osmotic pressure to actually push water up and make a fountain. And so it is a force that actually will move material against gravity. And there is a couple videos that are less than scintillating. However, they do exist. And you can actually see the effect of the sugar fountain pushing against essentially gravity. And so we don't really need our sound, but if you can see that, whoops, you can see it at home, but not in the room. Come on, computer. Come on. So basically she says, here's a sugar solution. Here's a sugar solution. Here's essentially a glass tube with a filter. It's actually a filter flask that she's got upside down, and there's a membrane being held on the bottom with that white block. And so again, since you've got two different concentrations of sugar, right, the concentration is higher in the tube than it is in the essentially pure water beaker that she puts it in. There's going to be a net flow from the beaker of water into the tube, right? And so as the water flows into the tube, it has to go up, right? But this is a real honest to goodness force that's actually pushing water up. So it's not, you know, some imaginary property. If you had a big enough force, you could push something big. It's not quick, right? Because again, it relies on the net statistical motion of the molecules across the membrane. So it's not like they all line up and start running across the membrane. And so there's now a time lapse of this. If we did this live, right, we'd have to start at the beginning of class and look at it at the end. You can see it's starting to move up there, and it actually moves up fairly far, but it takes about, if I recall, 20 or 30 minutes to do it. Right. But it is a real force. It's a real measurable force. But you're only going to see it if you have two solutions separated by a membrane. And so it's incredibly important biologically because of cell membranes. Right. Chemically, I could use the principle, right, if I needed to, but it's not a property that manifests itself simply because I happen to have a solution and I'm trying to do chemistry with it. Whereas the other three colligative properties we talked about, right, do in fact occur always simply by the nature that I have a mixture that I'm dealing with. Right, and so here we are. 12 minutes later, it's gone like 2 inches. Right, but there is the water pushing uphill. Right. Since I sort of mentioned it earlier, I'll mention it again, which is that sodium chloride in the environment is toxic. And the reason it's toxic is because of osmotic pressure, right? If you think in terms of now a cell, right? So, you know, organelles in here or whatever, right? This is essentially a salty solution. Inside the cell. If I put this cell in, for example, pure water, right? Since the membrane, the cell membrane is semi-permeable, the water can cross it. The concentration's higher in here, so the net direction of water is into the cell, right? Since it has pure water on one side and a solution on the other, it's trying to make them equal, but they're never going to be equal until they're ultra dilute, right? Because there's zero concentration on the outside. So if you do that, the cell absorbs water until it ruptures, right? And so you can cause the cells to lyse by putting them in what's often referred to as a hypotonic solution, meaning the concentration is lower than it is in the cell, right? On the other hand, you can do the exact opposite with good old salt. So if I got my same cell, right, and I submerge it in very salty water, right, now this would be what's known as a hypertonic solution, meaning the concentration outside the cell is higher than it is inside the cell. The cell will now try to dilute the salt, right? And so it shrivels and dies if the concentration of salt is high enough, right? The Roman legions used to do this to their enemies. Warfare used to be, far worse than it is today, right? So the Roman legions would march through, conquer their neighboring lands, and just to punish them and make sure they never rose up to oppose them, they would quote unquote salt the fields, which meant they literally dumped a lot of salt in the field so nothing would grow until eventually, over years or decades, right, rainfall diluted the salt and pushed it into the water table so that you could once again grow crops. Anything that tried to grow in the salty fields would essentially do this, right? The seedling might sprout, but then it immediately tries to dilute the salt around it and shrivels and dies. All right. Yes, no, maybe. Again, particularly if you are of a biological bent, you will see osmosis in that setting. In here, the other two cause phase change issues that we would have to deal with, but osmosis, we'd really have to go out of our way to express. Questions on any of that? Okay, so at that point, we sort of leave behind intermolecular forces and their implications for phase changes and turn to what I always think of as one of the three primary pillars of Gen Chem, which is kinetics. The three sort of big topics for Gen Chem, I mean, there's kind of four, I guess, if you want to include thermo, but the kinetics, equilibrium, oxidation, reduction reactions, and thermo are sort of the big four. Thermo is relatively small piece. Equilibrium is probably the biggest piece. But kinetics is sort of the first big pillar. And it's really about the speed of the reaction, right? Kinetics in general is the speed of anything, right? I drove here at 60 miles per hour. It's a speed, that's a kinetic measurement of my movement, right? And you see this all over the place. The book always picks This, for some reason, maybe because, again, it's biological, if you've ever had a lizard, seen a lizard, experienced a lizard up close, right, you will notice that lizards like warm rocks and hot sun, but they don't like cold. And if it gets too cold, the lizards go into hibernation. And the reason is really chemical kinetics, right? Reptiles are cold-blooded, which means their body temperature fluctuates with the external temperature. If it's cold outside for a lizard, it's cold inside, right? And cell functions are fundamentally all chemical reactions, right? And ideally, via evolution, smart design, or whatever belief system you'd want to use, right? The chemical reactions that drive the system are optimized for the normal conditions of the system, right? So a lizard functions best, right, in the rainforest in which it was originally evolved, right? And if you deviate the conditions, right, now my chemical reactions change their rate and I'm no longer optimized, right? And so the only response the lizard has to preserve its existence is to hibernate, because it simply cannot do its chemistry fast enough to do its normal metabolic activities, right? And so kinetics could be anything as a function of time, right? Kinetics is all about rate. Rates are change in something over time. And so you can define all kinds of different rates, right? I mentioned speed, right? That's really change in position, right? Distance traveled over the time it took to do it, right? You can measure reading speed in words per minute, right? Anything per unit time is a rate, right? For us, we're trying to measure the chemical reactions, right? And again, right, I remind you that chemical reactions are all about moles, 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 right? When I write my chemical reaction, right, what it's really talking about is number of molecules that react. So if A plus 2B equals 3Cs, right, that is one A molecule reacting with 2B molecules to give me 3C molecules, right? And of course, single molecule reactions are hard to do, so we tend to do them in large ensembles. And so we normally don't talk about individual molecules so much as moles of molecules, right? And so that's 1 mole of A's reacting with 2 moles of B's to give me 3 moles of C's. And it's worth pointing out, because it's something we'll need to talk more about on Friday, right? That is the net accounting for the reaction, right? By which I mean, it's telling me that the net change in particles is 1A, 2B's, and 3C's. It's not really telling me how the reaction happens, right? It could be a one-step reaction where literally 1A collides with 2B's to form 3C's, but it does not have to, right? That could be a 36-step reaction where all kinds of funky things are happening, but the net is 1A, 2B's, and 3C's, right? It could be a 2-step reaction where maybe an A collides with a B to form some reactive intermediate D, and then the D collides with another B to form the product, right? I don't really know how the reaction is happening from my balanced equation. What I know is the net change in quantities once the reaction happens, right? And we'll come back to that idea of mechanism on Friday. For now, I'm all about the accounting, right? And so, again, if I just counted the species present, right, as my reaction happens, 1A reacts with 2B's to form 3C's. So if just arbitrarily I started with 65 A's and 32 B's, right? The first time a reaction happens, I'm going to lose an A, right? I'm going to lose 2 B's, and I'm going to get 3 C's because that's what the balanced equation says happens, right? For the sake of time, let's say it took a minute for that to happen, right? After the first minute, I therefore have 64 A's left. I lost 1. I only have 30 B's left. I lost 2. And I now have, for the first time, 3 C's because I made 3. If I keep doing this, right, the A's keep dropping 1 at a time, the B's keep dropping 2 at a time, and the C's keep being formed 3 at a time. Eventually, I run out of B's because B is the limiting reagent, at which point everything stops. Right. What that means is if I'm actually trying to study the kinetics of this reaction, what I really need is a way to count one of the molecules. Right? If I can count the A's, well, I had 65. When I know I have 64, because of the reaction, I know I have 2 less B's. If I look later and there's only 49 A's, right, the fact that I lost 16 A's means I must have lost 32 B's because stoichiometry. And so if I want to study the kinetics here, I just need a way to count, measure the amount of any of the reactants, right? But you'll notice, right, the way they change is not the same, right? A is disappearing, B is disappearing, and C is appearing, which means I have minus A and minus B, but plus C, right? But because the stoichiometry is 1 to 2 to 3, I'm also losing different numbers of them. Whoops. And so, right, I can measure the change in amount, which is usually concentration for a solution because it's moles per liter, although it could be just moles. And there's actually 3 different rates I would end up measuring. Right? If I count the A's, I'm going to measure a change in A in some period of time. If I'm counting B's, I'm going to end up with a change in B's in some period of time. Right? And if I count the C's, I'm going to get a change in C as a function of some time. But the numbers for all 3 species are different because the stoichiometry is different. Right? And so if in that first minute I lost 1A, the rate of change of A is minus 1 per minute, 1 mole probably in this case. I'm doing them 1 molecule at a time, but typically a mole or molarity. In that same period of time, because of stoichiometry, the rate for B was minus 2 per minute. All right, and the rate of C was plus 3 per minute because of stoichiometry and the fact that it's a product instead of reactant, so I'm getting more instead of less as the reaction proceeds. All right. Now, this isn't terribly surprising, right? After all, I knew what the stoichiometry of the reaction was when I started. I have to be losing B's twice as fast as A or I'm not doing this reaction. All right. And it's correctable, right? Stoichiometry would allow me, even without measuring B, to know that if I measured the A to be minus 1 per minute, right, the B is minus 2 per minute because stoichiometry, right? But it would be confusing if we all chose a different species to measure and therefore a different species to report, right? I measured A because I did, and I tell you the rate's minus 1 per minute, 1A. right? You measured B and you say, hey, minus 2 Bs per minute. Sure, we can convert our numbers so we both understand them, right? But for the sake of simplicity in reporting, I can actually define a different rate, right, called the rate of reaction that is independent of what I measured. Because the only reason those numbers are different are stoichiometry. In the case of A and B and C, the sign's different because reactants versus products. So I can actually compensate for both of those, right, by taking into account the stoichiometry and taking into the side I'm on. So, there's all the fancy math you find in the book, right? In the end, what I'm going to do is simply correct for stoichiometry by including it up front, right? So minus 1A, or moles of A, per minute, I know for every mole of A or A, I do 1 reaction unit, right? Whereas I know for B, I do 1 reaction unit for every 2 Bs. And so I essentially normalize my measured rate for the stoichiometry of the reaction, and I can get rid of the sign issue if I just take the absolute value of everything, right? If I do that, I get the same calculated number no matter which rate I measured. And so that single corrected value is usually what's referred to as the rate of reaction, right? And so effectively, I have 4 rates here for this reaction. I have the rate at which A is reacting. I have the rate at which B is reacting. I have the rate at which C is forming, right? Those are the things I tend to measure in the lab because I'm watching the concentration of one of them. But in the end, I report the 4th one, which is the rate of reaction, because then we're both always reporting the same number and they directly compare without my needing to convert them, right? So the rate of reaction will always end up being positive because of my absolute value, and it always ends up being stoichiometry independent because I've normalized it relative to the stoichiometry of each species. Right. Yes, no, maybe. Right. And so you'll notice I did it for my whole little spreadsheet here. And sure enough, whether I'm in the A column, the B column, or the C column, once I take the absolute value and adjust for the stoichiometry, I always get exactly the same number across all 3 species. Right. And so I need to be very careful, quite frankly, in this whole topic, because the word rate gets thrown around like it's a confetti at a wedding, right? I already have 4 rates: rate of A, rate of B, rate of C, rate of reaction. I'm going to fairly soon, Friday, add to that rate law, rate constant, integrated rate law, right? And so everything's a something rate or a rate something. And so we need to be really careful about the rest of the phrase if I'm going to specify specifically what I'm talking about. But there's your hello to rate. We'll see what to do with it on Friday. If you have any questions or problems, give me a holler. Otherwise, I will go read your reflections.
Hello, Professor. I had a quick question on the project due next week.
Yep.
So I was looking at the rubric, and it says that you want to see if you can decide whether the chemical reaction we pick will work for this project.
Yep.
Is that saying we have to send you what reaction we're using beforehand, or you're grading on the premise that we have to be able to understand it by the end of the semester? I guess I'm just confused on what would really work for it. The only thing that would address that, I think, would be, it says if you're unsure whether you know enough chemistry by the end of the semester to understand, please ask. So are those two hand in hand, I guess, is what I'm saying?
If you give me something that I think's untenable, I'm going to tell you not to use it for the rest of the semester.
Yeah, but would we tell you that beforehand so like you don't write the whole paper on it, or is that just something we should do beforehand? Not pick a reaction that's obviously
Well,
not
you
doable.
you should not pick a reaction that's not doable.
Okay, yeah, I was just
Certainly,
wondering if
you
we
may
had
not know, in which case I'm going to tell you. But the idea is you're going to use it the rest of the semester. You pick something that's impossible, you make the rest of your semester impossible.
Are there
Right?
like further assignments based off this, or?
Every project is based off of this.
Oh, okay. Well, yeah, I didn't know that. All right. Well, thank you for the clarification.
Well, that's what it says up front, and why it was important to pick the. Right, it's right in the guidelines. I mean, it's important.
Is it? I couldn't. I didn't. I just must have missed it.
That's why it was important to pick a reaction that you could understand, because it's not really asking you to do anything with the reaction at this time.
Yeah. Yep.
Yeah.
I get that. All right. Thank you.
Yep.
Professor, I had a question just about that last slide that you showed us with the rates.
Yeah.
Why is the last rate not equal to the first two for the rate of reactions, the 10 over 58 minutes?
Because it's not. Yeah. Come back Friday to find out the details.
Okay. And then
rates in general are not constant, would be the short answer for now.
Okay.
But go ahead.
I thought it was like saying that no matter which way you solved it, you got the same rate of reaction.
I do, no matter which species I solve for.
Okay.
I didn't say anything about time. But go ahead. What was the other question?
Just about the video you showed us with the demonstrating the osmotic pressure as the liquid rose up the tube. Is that water that's rising up the tube, or the water is pushing something up the tube as it passes through the membrane?
I mean, there's water on both sides. I mean, the only thing that's different is the concentration of the stuff in the water. She's got sugar and food coloring in the glass tube, and it's pure water outside it. But essentially, I mean, you know, sugar, food coloring, and water is still 99% water.
So the water was both going through the membrane to the other side and going up the tube?
Yep.
Okay. Thank you.
Yep.
Have a good one, Professor.
Yeah, you too. Other questions before I get out of here? I do have office hours later if you need me.